Okay, good morning, everyone. This is Yuhao Chang from Academia Sinica, and it's my great honor to be the session chair of the best paper candidate session. And all the three papers presented in this session are best paper candidates. So please take care to the presentation and to guess which one will be the best paper award of today's of this year's NVMSA. And now I'm going to introduce the first paper's presentation. And the first paper is to minimize the age of information of NVRAM based the first paper will be the efficient and atomic durable persistent memory with 3-in persistent memory hybrid logging. And the speaker is Professor Xiangyin Zheng, and he is a professor in Academia Sinica, and he graduated from Pittsburgh University. And now please join me in welcoming Professor Zheng.
Xiangyin Zheng. Today I'm going to introduce our work, Efficient and Atomic Durable Persistent Memory through NPN Hybrid Logging. This is a joint work of National Taiwan University, Academia Sinica, and Macronex. Persistent memory has high density and can provide even comparable read performance. In addition, it is biodistressable and non-volatile. With these attractive features, it blurs the boundary between memory and storage and leads to a new memory hierarchy that offers performance advantage for data-intensive applications. As Intel announced the first persistent memory product, Intel Optane in 2019, the usage of persistent memory has come into the real world. The Optane sits on the memory bus along with different things, and these things are controlled by the integrated memory controller that is IMC in the CPU. And programmers can directly issue those instructions to access persistent data with the FAT direct mode. The main challenge of adopting persistent memory is how to maintain cache consistency efficiently. Most persistent memory adopt a transaction-like programming interface. A series of data updates in a transaction should be persisted in an all or nothing manner in case of system failure to achieve atomic durability. However, in modern memory hierarchy, the unpredictable cache line evictions and memory request reordering make it challenging to ensure atomic durability. Some modified data may arrive to the persistent memory earlier than other modified data within the same transaction. And if a system crash, some recent data will vanish, while some recent data will be persisted. So it fails to achieve atomic durability. Logging is a commonly used method to support cache consistency. It creates and persists a duplicate copy of data before any in-place updates, and use a log to recover data upon system crash. There are two types of logging, undo and redo. Undo logging records the old version of data before any write or in-place update. Sorry. And so the system can roll back to the original state if after a system crash. On the other hand, redo logging records the new version of data before write and in-place update, so that if a system crash, it can recover to the new state by replaying the redo logs. One common way to implement logging is through software. Programmers can manually add cache line flush and store fence instructions to enforce write ordering. Here we show an example of redo logging. The cache line flush instruction forces the cache to write back the logs to the persistent memory. And the store fence instruction ensures the logs are persisted before data are flushed back to the persistent memory. Although software logging can support cache consistency, it has several drawbacks. First, adding cache line flush and storage instructions increase the programming effort. And second, writing both log and data to the persistent memory induce the double write issue. It increased the write traffic on the memory bus, and the data drives will frequently fill up the writing queue. So the writing gen will be triggered very often. Since only writes can be serviced during the writing queue gen, the data reads will be delayed. Third, there are write order constraints. For example, in redo logging, the increased update cannot be performed before the transaction commits, and it lengthens the critical path latency. Several hardware mechanisms are proposed to ease the programming burden and accelerate the logging process. One promising approach is to move the persistent domain closer to the CPU and leverage the multi-versioning inherent in the memory hierarchy to eliminate log writes. For example, a prior work used an STRAM level cache to move the persistent domain up to the cache level. And another prior work, LAD, moves the persistent domain up to the memory controller level. The upper persistent level can be served as a read log area to keep the latest version of the data. And these logs in the upper persistent level are allowed to be updated to the persistent memory once the transaction commits. So ideally, there is no log write. And the cache level solution requires substantial hardware overhead because a large buffer is required to back the lateral cache, or an STRAM lateral cache needs to be used. In contrast, moving the persistent domain up to the memory controller induced lower hardware overhead as the battery backing requirement to back up the small writing queue is modest. However, it needs to fall back to the slow logging if uncommitted writes exceeds the small writing queue. In current Optane, cache consistency can be maintained via the software logging implementation in PMDK library. There are two generations of Optane, and both of them move out the persistent domain to cover not only the DIM itself. The first generation of Optane move out the persistent domain to the memory controller with the support of ADR. And with the support of ADR, write is persisted once it reaches the writing queue. Since the writing queue is small, the battery backing requirement is low. However, it suffers from the software logging overhead we mentioned before. And the second version of Optane moves the persistent domain up to the cache level with the support of EADR. So there's no need to add cache line flush instruction for cache consistency maintenance. However, it can alleviate software logging overhead, but however, it requires a large battery to back the entire cache. If we can design an efficient hardware logging mechanism on top of a system with ADR, we can fully explore the potential of Optane without the demand to equip a large energy storage. For systems with Optane plus ADR, as the persistent domain covers the memory controller, it seems the natural fit to leverage existing hardware logging mechanisms that assumes the writing queue is persistent. And LAD is the state of the art among this category of solution. As we mentioned before, LAD treats the writing queue as the redo log area and buffer uncommitted transaction writes in the writing queue. These uncommitted writes can be updated to persistent memory once the transaction commits. Ideally, there would be no log write. However, the writing queue has a limited size, and LAD needs to fall back to conventional logging when the writing queue is full. Joining each uncommitted write requires 3 steps. First, the old version of the old value is read from the persistent memory to the memory controller. Then a undo log is created and read to the log area in the persistent memory. And then the new data is increased update to the persistent memory. Therefore, the fallback procedure is slow because joining each uncommitted write needs to sequentially perform 1 read and 2 writes. And the interleaved read and write requests will induce frequent block turnarounds. In addition, the uncommitted write needs to stay in the ripening queue until the transaction commits or when the fallback is triggered. This lazy fallback makes the ripening queue easily full. If we can prepare a undo log and increase update the data before the ripening queue is full, we can save the space in ripening queue, and the ripening queue DRAM will be triggered less often. The performance degradation induced by the fallback procedure is exacerbated when the ripening queue is small. We can see that the throughput of LAD degrades significantly when the ripening queue size shrinks. And in particular, a prior study unveiled that the ripening queue in the Optane system is only 512 bytes, much smaller than the 4K byte ripening queue in conventional DRAM systems. Therefore, we need a new design better tailored to the practical persistent memory architecture as Optane DIMM. To this end, we propose an NPN hybrid logging mechanism that exploits the features of Optane DIMM to perform logging efficiently. Optane DIMM has some unique features. In addition to the persistent but small ripening queue, each Optane DIMM has the unDIMM persistent memory controller, that is PMC. The PMC is much more complex than the simple DRAM DIMM because it needs to perform internal access translation for wheel leveling and manage multi-level inclusive buffers to exploit spatial locality and coalesce writes. The PMC communicates with the integrated memory controller on the CPU through the DDRT protocol, and access to Optane media are controlled by the media load store. Similar to prior studies, we can leverage the persistent ripening queue as the redo log area. And our key innovation is to prepare undo logs in the background using the persistent memory controller by NPN copy to solve the ripening queue overflow challenge. Our goal is to provide comparable read-write latency as non-persistent ones while maintaining crash consistency. Here shows the overview of our design. The persistent ripening queue is treated as the redo log area. When the transaction writes to L1 cache, a copy of data is persisted in the ripening queue as a redo log, and the written cache line is marked with a T flag to indicate it is written by a transaction. The redo log in the ripening queue is marked with an R flag and an ID to indicate whether it is uncommitted and the redo log is from which core. Data written by transactions can be discarded when it is omitted from the lexical cache, as it is already persisted in either the ripening queue or the persistent memory. And to solve the inefficiency of previous fallback procedure, we leverage the persistent memory to support in-memory copy, so that undo logging can be done in the background. The PMC prepared undo logs by NPN copy, and then in place updates the data based on our redesigned scheduling policy. The impact of exploiting the PMC to perform NPN undo logging are twofold. First, it allows an uncommitted write to turn into an in-place update as long as its own base data is already copied to the log area by the background NPM copy. This relaxes the write order constraint. Second, it alleviates the double write issue. Although the persistent memory media is still written twice, however, the write traffic on the memory bus is reduced. There is no local write traffic on the memory bus, and so the writing queue will be gen will be triggered less often to mitigate the bus turnaround delay. Here we use an example to illustrate the process of our design. When the transaction writes A to the L1 cache, a copy of A is persisted in the writing queue as a redo log. Then the undeemed PMC then copies the whole data of A to the log area in the background through an NPM copy. At the same time, the transaction can continue to write B to the L1 cache, and a copy of B is persisted in the writing queue as a redo log. After the NPM copy of A is done, the redo logs of A in the writing queue can turn into an in-place update and be written to the persistent memory if the writing queue is empty. Meanwhile, the transaction can proceed to write C, and the PNC can perform an in-place copy to prepare an undo log for B. This early in-place update of A relaxes the write order constraint and can make the persistent write be tagged by non-persistent ones and prevents the writing queue from becoming overflow. During this process, if the level cache runs out of space, the data could be if level cache runs out of space, the data written by the transaction can be discarded directly to avoid writing persistent memory twice. When the transaction commits, all its redo logs can turn into in-place updates, and all its undo logs can be invalidated. If a system crash occurs, redo logs are discarded from the writing queue, while the remaining requests needs to be persisted to guarantee that committed writes are persisted. In the following, I will explain some key implementation of our design, and you can check our paper for more details if you are interested. Our design aims to prepare undo logs in the background without interfering with non-traditional requests. So to prevent delaying reads, we modify the scheduler at the memory controller to determine the priority among read, write, and undo log preparation requests. Once the scheduler decides to prepare an undo log, the IMC issues log prepare, a new DDRT protocol command we propose to notify the persistent memory controller. After PNC receives the log prepare, it gets a new log entry from the protocol log tail pointer and perform NPM copy. Depending on the data location, we propose two NPM copy modes, inter and intra-bank copy. We also carefully design the log format and the allocation policy to maximize the usage of the fastest NPM copy modes. And when the transaction commits, another transaction commit TDRT command will be sent to the PNC to invalidate the undo log of the committed transaction. Since preparing undo logs during writing queue gen will lengthen the delay to the pending reads in the repending queue, we follow two design principles to redefine our scheduling policy. First, when reads have the highest priority, we reschedule the undo log preparation and in-place updates of the redo logs eagerly before writing queue gen if the writing queue is empty. Second, during the writing gen, undo log preparations are avoided unless uncommitted redo logs stuff the entire writing queue. That is, if there are no more writes, we will gen no more writes until all the buffer normal writes are issued. In this case, the redo logs could stay in the writing queue longer to wait for commit to reduce undo log preparations. If all the buffer requests are redo logs, Then we drain until the repertoire is empty to make room for incoming requests. The complex PNC in Optane can be leveraged to implement impedance copy, and we designed two types of impedance copy modes based on the location of the source data and the destination address. The first type is interbank copy. The PNC first activates the source and destination rows concurrently, and then perform impedance copy via the persistent memory chip I/O and the transfer command we newly added. Since the activation of source and destination bits can be overlapped, and the turnaround latency, the bus turnaround latency can be saved compared to the baseline. So the interbank copy mode is very fast. Another impedance copy mode is intrabank copy. In the intrabank copy mode, we'll copy 64 byte data from the source row from the source row to the destination row in the same bank using the media load store. It is lower than the interbank copy mode, but it can still save the bus turnaround latency over the baseline. To enable efficient impedance log management, we proposed a design different from prior work. First, instead of allocating a continuous address space as a log area, we pre-allocate a dedicated address space with the same bank ID to store and do logs in a single bank and store data in other banks, so that we can leverage the fastest interbank copy mode to prepare and do logs. Second, as the transaction on different cores usually execute concurrently, we aim to allocate log entries of different cores to share the same persistent memory row to increase the row buffer hit rate. In addition, we train different from the conventional design that usually use a circular buffer to manage the logs. We train the undo logs of different cores separately with per core log head and tail pointer to accelerate the undo log invalidation. We implement and evaluate our design using the second average Gen 5 plus the NVMe simulator. And the evaluate benchmarks include both widely used kernels and the macro benchmarks from Whisper. And we classify the workloads into two groups, small transaction and large transactions. We compare several hardware logging designs, including DHTM, which is a baseline hardware redo logging approach that has the double write issue, and the LAD that is a state-of-the-art multi-versioning design. And also the hybrid LAD that is our design, but undo logs are lazily prepared only during writing to gen. And our hybrid design, and in addition, we compare with LAD infinite, that is LAD, but with unlimited writing queue size, so that it can serve as a performance upper bound. Here we show the transaction throughput normalized to LAD infinite. LAD performs better than DHTM for small transactions, and since it can alleviate the double write issue. However, for large transaction workloads, which saturates the writing queue quickly, LAD often need to fall back to the slow logging task, so it performs worse than DHTM. Compared to LAD, our hybrid improves the performance by 70% and 40.4% on average for small and large transaction workloads. The benefits of preparing undo logs by impedance copy to eliminate the bus turnaround overheads can be observed by comparing hybrid LAD with LAD. And another fold of benefits of preparing undo logs in advance to alleviate writing queue saturations can be observed by comparing hybrid and hybrid LAD. One of the major benefits of design is reducing the write traffic on the memory bus. This figure shows the number of logs and transaction writes passing through the memory. So passing through the memory bus normalized to LAD infinite. The proposed hybrid does not have log writes as expected. For DHTN, the total writes are about 2 times of the transaction writes, as it has double write issue. The state-of-the-art LED needs to fall back to the slow logging path, so the total writes almost double that of the transaction writes on large transaction workload. Our design can also effectively reduce the wrapping queue frequency by eliminating log writes and preparing undo logs in persistent memory. So DHT, as shown in the figure, DHTN has the highest wrapping queue gen frequency. For small transaction benchmarks, LED and hybrid have similar wrapping queue gen frequencies. However, for large transaction benchmarks, the wrapping queue is easily saturated, and the advantage of hybrid over LED becomes significant. In summary, we propose the first NPN hybrid logging mechanism that takes advantage of Intel uptending to perform logging efficiently. The persistent wrapping queue in the integrated memory controller is treated as the redo log area. To solve the wrapping queue overflow challenge, undo logging is done in the background while the NPN copy implemented at the DIN controller. The scattering and log allocation policies are carefully designed to accelerate the logging process. As a result, we can provide higher performance compared to the state-of-the-art, and our design induces most hardware overhead compared to the already complex persistent memory controller. In addition, we don't need an additional power storage to back up the entire cache. Thank you for your listening, and I'm happy to take any questions.
Any questions? Any question? Okay, first I would like to ask one question. This is a very interesting talk, and it seems that the proposed solution is very novel and workable. But I have one question is that because we usually know that the CPU has multiple layer cache, but in your design, it seems that you only mentioned one cache in your design. Is that the multiple level cache layers will affect the correctness of your design, or it is just adapted to? It is also corrected to the real CPUs.
Our design can be applied to any the system with any level of cache. Our design only modify for the cache hierarchy part. Our design only add a flag per cache line in the cache hierarchy. And similar to other hardware logging mechanism, we just copy the L1 cache controller needs to create a copy when the data is written, and the copy will be persisted to the wrapping queue. And the next level cache will discard the transaction writes, and the middle layer of the cache is not impacted by our design.
Okay, thank you. Any questions? Okay, I have another question. In your design, it seems that there are a lot of operations in doing the login and unlogin. What's the major overhead in your design?
The major overhead of our design, actually, our design can leverage most of the data paths in original persistent original uptending, but we need to add some additional commands like 2 DDRT command and 2 uptending command.
Okay, thank you. Because the time is up, so let's join us to thank Professor Chen again. Thank you. Now we're going to introduce the second talk in this session. Because this talk is pre-recorded, and the second paper is called the buffered hash table, leveraging DRAM to enhance hash index in the persistent memory. And the speaker is Praj Chala from University of Texas at Arlington. And now let's look at the pre-recorded video. And if you have any questions, you can post it on the message box of the WebEx. Thank you.
Hello everyone. In this talk, I'm going to present buffered hash table, leveraging DRAM to enhance hash indexes in the persistent memory. What we present is a hybrid index design that uses DRAM as an auxiliary medium to reduce write amplification of persistent memory index structures. I am Prajwal Challa. This is a joint work with my peers Chen Zhang and Xingshan Zhao, along with our supervisor, Dr. Song Jiang. We are from the Department of Computer Science and Engineering from the University of Texas at Arlington. The introduction of persistent memory has challenged the dichotomy of performance and persistence. Having both DRAM-like speeds and ability to persist data, also while providing both larger capacity and lower cost compared to DRAM, persistent memory has gathered the attention of both industry and academia alike. These unique blend of features made persistent memory the ideal medium to migrate in-memory index structures, and many efforts were made to do so. Simply migrating index structures from DRAM to persistent memory is not enough, as it is reported that the index operations may account for 14 to 94% of queries execution time in today's in-memory databases. So, the performance of these index structures in persistent memory is of crucial importance, and we need to make every effort to improve the performance of in-persistent memory indexes fast. The exploration of performance of indexes in persistent memory was skewed by the unavailability of real persistent memory devices. Consequently, much attention was given to make in-memory index structures crash consistent, as in-memory index structures by default do not provide crash consistency. This focus on crash consistency was based on the premise that all persistent memory is just slower but persistent DRAM. Upon its release, numerous studies have confirmed that Optane DC persistent memory, the first commercially available persistent memory, accessed data to and from its 3D X-point media at a 256 byte granularity. This property makes Optane DC persistent memory, PMEM for short, behave like a block device. And similar to a block device, any write smaller than the 256 byte access granularity leads to a read-modify write of 256 bytes, leading to a potentially large write amplification. Studies have also noted that the PMEM's throughput is observed to be at its peak when writes to it are large and sequential. Index updates, on the other hand, are usually small and random, and such updates do not align with the peak performance scenario of PMEM. Let us take a closer look at the performance of PMEM under different access scenarios. To observe the performance variations for different access patterns in PMEM, we ran an experiment where we use a bucket-based hash table in PMEM and populate it with two different methods. In the first experiment, the sequence of keys are hashed randomly into different buckets until the buckets are full. By default, hash function attempts to scatter keys evenly across different buckets. So this case represents the actual scenario one would expect in a real-world usage of in-PMEM hash table. Then, for the second method, the sequence of keys are carefully arranged so that the buckets are filled sequentially one at a time. This way, we attempt to write to each bucket continuously and sequentially. This is an unrealistic scenario as the keys have to be carefully arranged, and such arrangement as is highly unlikely in the real world. The throughput performance of the sequential write experiment is shown in the plot to the right. The y-axis is the throughput performance in millions of operations per second, and the x-axis is the bucket sizes used in the experiments, which ranges from 64 bytes to 512 bytes. We can see that the throughput performance of sequential writes improve as the bucket sizes increases. However, when we move to the real-world scenario of random writes, the throughput performance is significantly lower than its corresponding counterpart of sequential writes. This disparity of throughput performance can be analyzed using write amplification in PMEM. During the experiment, we measure the amount of data written to the PMEM media. Using this information, we quantify write amplification in PMEM as the ratio of amount of data written to the PMEM media and the amount of data written to the hash table. The write amplification is presented on the Y2 axis. We can observe that random writes have a consistent high write amplification. As the workload used is much larger than the PMEM's internal write combining buffer, each random small write has to be written individually to the PMEM media, each of which triggers a 256-byte read modify update. On the other hand, for sequential writes, the write amplification is much lower compared to random writes. When the bucket size is a multiple of PMEM access unit, we observe the write amplification is just 1. As PMEM's internal prefetching mechanism assists to accelerate the read modify write operations, an increase in throughput performance for sequential writes is observed as the bucket sizes increases. Given these observations, it is tempting to consider few straightforward solutions to reduce write amplification in PMEM. One such solution is to allocate a DRAM buffer to stage writes into PMEM for each hash bucket. This way, the write amplification can be reduced. The drawback of this approach is that DRAM is not only limited but also a highly contested resource. So, a DRAM buffer, if applied, should only be for large PMEM space and only onto spaces that are write intensive. Another simple solution is to just let the operating system handle buffering for PMEM, as operating system already manages buffering for disk writes. The issue in this approach is that PMEM is directly accessed by the processor and the cost of OS involvement becomes prohibitive. So buffering needs to be part of the data structure. If ample amounts of DRAM is available, then a simple approach might be to always allocate a buffer, as it is guaranteed to improve performance. The ideal solution should consider the case that if addition of buffer degrades the performance in certain scenarios, the buffer should not be applied in such scenarios. And finally, it is always tempting to design a brand new approach to manage buffering in PMEM. However, such approaches present a roadblock to existing in-use designs. A general approach that can help existing designs will help portability. So, an ideal solution should have the following design goals. First, a design that can be integrated into existing PMEM hash index designs. The approach should not excessively assume availability of a particular structure or algorithm design in an index where it will be applied. Instead, its design features and advantages should be retained. Second, buffers are to be integrated into a PMEM index structure in a straightforward way. The buffer operations and management should be decoupled from those in an existing index as much as possible. Third, write buffers are allocated to large chunks of PMEM areas which receive writes. Fourth, the presence or absence of DRAM should not degrade the original performance of PMEM index. With these design goals in mind, we built a generalized approach that can reduce write amplification in PMEM index structures. Our implementation represents a case study on hash index using the general approach. Buffered hash table, BHT for short, is the hash index implementation of the generalized approach. BHT is a DRAM PMEM hybrid hash table design that incorporates in-DRAM write buffers to collapse writes before writing to PMEM, effectively reducing write amplification. BHT is implemented on top of a state-of-the-art PMEM hash index design called Cache Line Conscious Extendable Hashing, CCEH for short. CCEH is an advancement of extendable hashing where it uses an intermediate layer in between directory and buckets. Each bucket in CCH is a unit of cache line which is 64 bytes. To reduce the directory size increase of extendable hashing, CCH uses collection of buckets called segment to manage data. Segments are indexed by G most significant bits, while buckets are indexed by using L least significant bits of the hash key. As segments in CCH represent a contiguous memory chunk that receives random accesses, buffered hash table logically attaches a buffer to segment in CCH. While maintaining the performance features of CCH, integrating buffers brings few straightforward changes to the original design of CCH. Let us take a closer look at the workings of BHT. Any writes to the segment in PMEM are first received by the buffer. Once the buffer is full, all the key value items in the buffer are written to segment in batch. This operation is called flip. However, during the flip operation, the following issues arise. First, buffering the key value items into DRAM and then writing them to segment in PMEM does not guarantee that the writes are sequential. Second, reads to the segment have to be blocked for the entirety of the flip operation. And third, very expensive flush fence operations have to be performed for data integrity within the segment. To address these issues, buffered hash table will first create a copy of the segment in DRAM before the contents in the buffer are written to PMEM. To this in DRAM segment copy, the data in the buffer is inserted. Any update needed operations are processed at this point. This in DRAM segment is then written to persistent memory. This segment is written to PMEM as a new segment rather than overwriting existing one. This batched out-of-place manner write allows both sequential write and concurrent reads during the flip operation. This approach also removes the need for expensive flush fence operations for data integrity in the segment. As the new segment is written in a batched out-of-place manner, the pointer of the CCH directory pointing to the old segment needs only one atomic pointer switch to point to the newly written segment in PMEM. Even though BHT allows for sequential writes and concurrent reads and also avoids the need for the expensive flush fence operations, the design must accommodate for any scenarios where integrating buffers degrades the performance, and such a case should be handled for the efficient utilization of the buffers. A buffer is only efficient when it is attached to a PMEM space that is write intensive. Using the buffer for a read intensive workload is not only inefficient utilization of DRAM but can also degrade the performance. Each read miss will first hit the in DRAM buffer and then the PMEM, adding additional overhead. To avoid degrading the original read performance, a counter is maintained which tracks the number of read misses to the segment. Once the counter reaches the threshold, the contents of the buffer are flipped, even in the case that the buffer is not full. Subsequently, reads directly go to the PMEM. To efficiently use DRAM after a certain number of counter overflows, the buffer is removed from the corresponding segment. Only a minimum number of buffers are retained to track changes of write intensity. Now let us take a look at the crash recovery in BHT. As key value items are first received by in-DRAM buffers, there exists a possibility that the system crashes before the items in buffers are persisted into PMEM, resulting in data loss. To prevent such a scenario, BHT maintains a log in PMEM. All inserts sent to buffers are also appended in the log. Unlike traditional disk-based logs, PMEM's 16 kilobyte internal write combining buffer removes the need for additional DRAM space for writing to log. After the contents of the buffer are persisted to PMEM, that is, after the flip operation, the items of the buffer are considered garbage in the log. To improve the efficiency of garbage collection, BHT tracks the oldest non-garbage item for each buffer, and all items before this oldest non-garbage one can be removed. The experimental setup. All experiments are performed on a server containing Intel Xenon Gold 6320 CPUs. The server is equipped with 188 gigabytes of DRAM and has 6 first-generation Intel Optane DC persistent memory, each of which has 128 gigabytes of capacity. We use NVMSA to pin threads to cores, and for all experiments, a uniformly distributed 120 million key-value item pure write workload is used. Each key and value are 8 bytes each. Let's first evaluate the performance of buffered hash table against state-of-the-art. Buffered hash table is compared against two state-of-the-art PMM hash index designs, CCH and Dash. Dash is a dynamic PMM hash table design that uses techniques like fingerprinting and optimistic locking to achieve high performance. For accurate comparison, default configurations for both state-of-the-art designs are used. In this experiment, each segment receives a buffer in buffered hash table. The throughput in millions of operations per second is presented on the y-axis and the number of threads is presented on the x-axis. At 40 threads, BHT outperforms CCH by 2.3 times and Dash by 2.8 times respectively. It can be observed that BHT has better performance compared to both CCH and Dash even at low thread counts. As both CCH and Dash allow in-place updates directly onto the PMM, a large number of small random writes limits the throughput performance of these indexes. Buffered hash table, on the other hand, uses buffers to batch writes to PMM in a batched, out-of-place manner to extract PMM's peak sequential write rate. The performance gap can be explained by analyzing the bandwidth of PMM. Bandwidth is defined as the amount of I/O on the PMM. The PMM bandwidth is shown in the plot to the right. The ratio of corresponding throughput and bandwidth for an index infers the I/O amplification. As BHT batches writes, which are aligned with PMM access unit, BHT reduces the expensive bandwidth consumption by PMM. CCH and Dash, which allow in-place updates, see a spike in bandwidth consumption as each random small write triggers a 256 byte read modify write operation. Given ample DRAM space, we can see that BHT gives high throughput performance. Now let us see the impact of DRAM size and availability. To understand the performance of adding in DRAM buffers, we explore the performance of BHT with varying buffer sizes. In this experiment, each segment is equipped with a buffer. A fixed number of 20 threads is used in this experiment. Buffer sizes are on the x-axis and the throughput is on the y-axis. As the buffer size increases, we see that the throughput of the buffered hash table increases. This result is coherent with the observations of representative hash index experiment, where large buffer size corresponds to higher throughput. Now, observing the amount of PMM I/O, we can see that an increase in the buffer size helps transform more number of random writes into batch sequential out-of-place writes, leading to a higher throughput. As DRAM is not necessarily guaranteed to be available, we measure the impact of DRAM availability on BHT. We use buffer ratio to define the number of segments that have buffers. If each segment has a buffer allocated for it, the buffer ratio is 100%. We can see that the throughput performance where each segment receives a buffer is the highest achieved. However, even with just 40% of the segments having buffer, BHT achieves around 1.6 times the throughput improvement compared to having no buffers. Analyzing the PMM write I/O at no buffers to 100% of the segments having buffer, we observe the write amplification is reduced by 2.1 times. These results suggest that integrating buffers to an in-PMM index design helps tackle write amplification even with meager availability of DRAM. To conclude, we present a DRAM PMM hybrid hash index design that uses in-DRAM write buffers to coalesce writes to reduce the write amplification in the PMM. Based on experimental evidence for representative hash index design, we construct a generalized approach that can be integrated into existing PMEM hash index designs. Our implementation on a hash index shows that the throughput performance is improved by a factor of up to 2.3 times and 2.8 times compared to state-of-the-art hash indexes CCH and dash respectively. Thank you very much.
Thank you for your amazing work. It's really amazing that it outperformed the state of the art. I'm just curious, what is the impact of the write ahead log? What is the write amplification caused by the WAL?
Oh yeah, so adding a write ahead log in PMM does induce a bit of overhead, but our performance that we have shown already includes those the cost of write amplification caused by the log. So we are able to achieve higher performance even though we maintain the log itself, and all the experimental results that we have shown already include the cost of the log.
Another question is that how does the BHT integrate into existing data structure? How much is the modification, code modification required?
Oh, usually that is kind of dependent on how you are implemented and what types of specific details that each of the existing index structures offer. So the implementation varies quite a bit, but our implementation is not too evasive. Like you don't need to necessarily change too much of the existing code base to integrate our stuff. I'd say it's not too heavy.
Okay, thank you.
Thank you very much. Thank you.
And thank you for the speech. Can you once explain why the proposed method has lower P memory throughput in the experiment? Does this mean this work has better performance? Thank you.
Okay. Pardon me, can you just repeat the question?
In the experiment, I think you show that your work has a lower throughput in the PM memory. I think it's in your one of figure show that. Does this result show that your proposed work is better?
I don't necessarily believe where BHT actually has lower performance compared to the state of the art. What we observed was that even at lower thread counts, BHT's throughput is higher than the corresponding state of the arts like CCH and dash that we have compared against. And primarily the reason why we have better throughput is because we do a batched sequential out of place write. So we are able to take advantage of the CCH. We are able to take advantage of the PMM's block access unit, which is 256 byte. But CCH and dash, the state-of-the-art index structures, on the other hand, allow in-place updates, which trigger a lot of read modify writes. Each write having 256 byte read modify write updates. So consequently, they have lower throughput compared to what we have, even at lower thread counts.
Okay, thank you.
We have another question.
Thank you for the great work. I have a short question about this work is based on the implementation of CCEH, but to my knowledge, Dash is work that is designed directly for Octane, and in the evaluation show that the CCEH have better performance than Dash. Do you have any idea on how why does this happen? Thank you.
Oh yeah, so I believe one of the reasons that could be the reason is that when Dash actually evaluated against CCH, they had the CCH version was kind of old. What we are using is the latest implementation of CCH provided by the authors. So I believe that could be one of the reasons why there is a disparity between CCH and Dash performance.
Okay, thank you very much. And actually, we have some out of time, so let us to thank try to work again. Thank you.
Oh, thank you very much. Thank you. Yeah.
Hello, everyone. I'm glad to have the opportunity here to present our work, HNFFS, Revisiting the NOR Flash File System. The contents of today's presentation are fivefold, including background and introduction, motivation, the key designs of HNFFS, and I'll present evaluation result, and finally summarize HNFFS. NOR Flash embraces its new age due to the coming of the IoT era. NOR Flash is one long-established and classical non-volatile memory storage. Nowadays, NOR Flash is widely adopted in IoT scenarios such as 5G base station, portable products, and so on. Recent market report shows that although NOR Flash memory represented only 4% of the total flash memory market in 2021, the sales of NOR Flash devices soared by 63% last year to $2.9 billion. The figure below shows the leading suppliers in NOR Flash memory sales, which further proves the values of NOR Flash's researches. Compared to widely known NAND flash, NOR Flash is better addressable, smaller, and more reliable. It is erased in sector unit and its erasing life cycle is limited. Generally, NOR Flash is usually used for resource-restricted IoT devices. Here is a table which compares NOR Flash and NAND flash. There are multiple ways to access NOR Flash, like using row commands or using file system. File systems provide general interface for accessing NOR Flash, which is kind of the best choice. Nowadays, there are two representative NOR Flash file systems. One is generally Flash File System 2, JEFS2. The other is SPI Flash File System, SPIFS. In this talk, we'll discuss the issues of these two NOR Flash file systems and talk about the design of our Harmony NOR Flash file system, HNFFS. It achieves both NOR Flash and IoT device friendly. Moreover, we make further evaluations with JEFS2 and SPIFS in multiple dimensions. Let's give some analysis of JEFS2 and SPIFS. The first is JEFS2. It represents a series of NOR Flash file systems that keep their indexing structure in DRAM. The figure below shows its structure. JEFS2 regards each data as a data entity and uses a large read-black tree in DRAM to index them in a file logically. However, JEFS2 has 4 problems. First is its slow recovery time. It must perform 4 media scanning to build its physical ledger. The second is JEFS2 only performs garbage collection in write paths, which not utilizes system's idle time and thus suffers heavy foreground GC overheads. Third, read-black tree consumes a large amount of memory, which is not friendly to IoT devices. Lastly, JEFS2 uses a pure random victim selection algorithm to perform its wear leveling. This suffers poor wear evenness. Next, we talk about SPIFS. SPIFS represents a series of NOR Flash file systems that use restricted DRAM resources. It keeps index node in the NOR Flash and maintains only one index node in the DRAM as cache. This leads to long indexing latency. Besides, SPIFS uses a pure static victim selection algorithm to perform wear leveling, which requires to scan all the sectors, and thus its performance is bad. Other flash file systems, like UBIFS or F2FS, UBIFS needs to maintain a UBI layer to provide scalability and reliability, but this introduces large extra memory usage. While F2FS builds an unblock interface, requiring hardware-supported flash translation layer to provide hardware-based wareletting. These file systems are designed mainly for NAND flashes, and their design can hardly apply to NOR flash file system. In that case, based on our observations and motivations, we propose HNFFS. HNFFS has several key design considerations. For performance considerations, HNFFS is built as a log-structured file system and based on JEF2. To reduce recovery time, HNFFS applies erasable sector summary node at the end of each sector. To reduce heavy foreground GC overhead, HNFFS adopts an adaptive GC mechanism which utilizes system's idle time. Further, to reduce memory usage, HNFFS designs a mergeable tree to dynamically merge indexing nodes. Finally, HNFFS combines random and static wareletting to provide trade-offs between wareletting performance and evenness. Others, like data atomicity, consistency, we've talked them in our paper. Please see our paper for more information. We now talk about HNFFS architecture. In the consideration of NOR flash's characteristics, HNFFS is built as a log-structured file system. We regard all the data as a node with header and body. Each data write is done sexually to be NOR flash friendly. The figure at the left below shows the node structure. Further, to avoid random access to NOR flash, HNFFS builds an inode table in DRAM to record the node's physical location and their meta informations. To build a high-performance NOR flash file system, we also build a tree-based index structure for each file for fast indexing. Besides, HNFFS also combines random and static wareletting to provide trade-offs between wareletting performance and evenness. Next, we talk about our breakdown optimizations. At first, HNFFS needs to scan whole NOR flash to build inode table to recover its system, which is slow. In the IoT scenario, slow recovery time can be harmful to user experience. Our solution is to put a summary node at the end of each sector. The summary node maintains meta information of all the nodes in the current sector. During recovery, HNFFS scans summary node, then it can fast locate the nodes on the NOR flash and rebuilds inode table in the DRAM. Then we talk about adaptive GC technique. It is used to mitigate heavy foreground GC overheads. To achieve this end, it combines foreground and background GC. For foreground GC, it is triggered in the right path when there are no space to reserve. In our implementation, we pre-reserve 5 sectors to guarantee GC is working fine. Then we use random static wareletting algorithm to choose a victim sector. Finally, we migrate all the valid nodes from victim sector to other valuable sectors and erasing the victim sector at last. For background GC, resource limitation is one of the most important factors to be considered. We should keep that in mind. In that case, we trigger background GC when there are no write requests and set 2 rules to restrict its resource consumption. Rules number 1, we set a trigger threshold such as 13% of system utilizations. Only if the threshold is approached, we activate the background GC. Rules number 2, to avoid running background GC too aggressively, we trigger it each 30 microseconds. Moreover, to prevent consume too much CPU resources, background GC only migrates 1 valid node from victim sector per pass. Limited memory should also be taken into consideration in IoT scenarios. However, generating each small write indexing node is memory inefficient. Theoretically, to handle 10,000 times write, 10,000 indexing nodes are required. The smaller the write is, the more inefficient the memory utilization is. We propose mergeable tree as our solution. It has two basic principles. The first principle is try not to index small data. We try clean the small indexing nodes by merging logical sequential small nodes in the index structure at runtime. This also reduces NOR flashes space. See the figure below. These two black indexing nodes represent two physical nodes in the NOR flash. By merging them, we rewrite a node range from 0 to 629 into NOR flash and evict the old ones. In fact, defining small data is not easy. This depends on different workloads. In that case, the second principle is to configure small data dynamically. To achieve the principles aforementioned, we maintain a merge buffer in DRAM, which is implemented as a simple array. The general workflow is, first, to configure and identify small data. We use a traverse thread to sample the red-black tree every 100 write requests, and it chooses the most frequent data size as a threshold of small data. If the size of the next write is small, the HNFFS inserts the indexing node into red-black tree and locates a slot in merge buffer to reference it. Finally, if the merge buffer is full, we merge the logically sequential nodes as the same way as before. And thus, the mergeable tree can reduce a lot of memory usage and reduces NOR flash space. Then we talk a little about the random static wear-leaving algorithm. The truth is that either random or static wear-leaving has bad wear evenness or bad performance. HNFFS uses a simple method to combine these two strategies. We first categorize sectors into 3 levels. Dirty levels means there are invalid nodes in this sector. Clean sector means there are nodes, but none of them are invalid in the sectors. Free sectors means there are no nodes in the sector. Random static wear-leaving starts from randomly picking victim sector. There are 95% probability for choosing dirty sectors and 5% probability for choosing clean sectors. Such random strategy might cause a problem. If chosen clean sector is erased more than other dirty sectors, then we should choose dirty sector as victim instead, but not this clean sector. In that case, to make sure we are keeping wear evenness, we do further check by carefully comparing the erase count of the selected level with the other level. For example, if random static wear-leaving chooses clean sector, then comparing it with other dirty sectors. Otherwise, comparing with other clean sectors. At last, the least erasing count sector is chosen and returned it to the caller as victim sector. Finally, we present our evaluation result. We implement HNFFS on Linux OS. Besides, to accomplish experiments, we also migrate JEFS2 and SPIFs and write a testing file system program on Linux OS. Linux OS is one real-time operating system developed by Beijing ACO Info. Due to device limitations, we evaluate on a NOR flash simulator provided by Linux OS Development Kit. The emulated platform is Milling 2440. We compare HNFFS with JEFS2 and SPIFs. The table below shows the NOR flash environment for experiments. At first, we try to figure out how does the erasable sector summary improve recovery time. The figure below shows the result. Mount 55% indicates recovery under 55% system utilization. In the figure, we can see that HNFFS achieves 1.2 to 1.6 times recovery performance compared to JEF2 and SPIFs. And SPIFs shows best recovery performance because it does not build in DRAM structure to locate physical data. Next, we study how does adaptive garbage collection contribute to HNFFS GC. The figure shows the result. Note that GC-0.5 to 0.3 means preoccupying 15% system space, then write data of 13% system space, 4 KB per write, and 1 second between each request. In the figure, HNFFS shows better write performance than JEF2 due to it is reducing 38 to 77% nodes migration by the foreground GC, thanks to background GC. Next, we know how does mergeable tree save memory and improve write performance. The experiment is conducted by producing 16 to 128 byte data 10,000 times. There are 15% 128 byte data for each 100 write requests. The figure shows the results. In the figure, we can see that HNFFS achieves up to 2.3 times and 6.04 times performance compared to JEF2 and SPIFs respectively, because it lowers the head of indexing tree in memory. And HNFFS saves about 93% memory compared to JEF2 because HNFFS merges small data nodes at runtime. At last, we know the trade-off brought by random static wear-leaving algorithm. For better observation, our evaluation is based on a 128 MB NOR flash emulated on Windows, 16.4 KB per sector and 2048 sectors in total. We write 3 times 128 MB data. Each data size is less than 16.4 KB. If NOR flash is full, we delete written data randomly and trigger foreground GC to clean up NOR flash's space. The figure shows the result. In the figure, the variance of each wear-leaving algorithm is 0.12, 0.04, and 0.31. And the random static wear-leaving causes the least erasing count. Besides, random static wear-leaving achieves 1.3 times performance compared to static wear-leaving algorithm. Finally, we summarize our work. In the consideration of NOR flash characteristics and its efficiency, we built it as a log-structured file system with any DRAM indexing. To reduce recovery time, HNFFS puts erasable sector summary node at the end of each sector. To reduce foreground GC overheads, HNFFS leverages systems idle time to pre-perform GC with some rules to limit resource consumption. To save memory usage, HNFFS merges small data nodes at runtime by leveraging mergeable tree technique. Lastly, HNFFS combines random and static wear-leaving algorithm to provide trade-offs between performance and wear evenness. We have implemented HNFFS in Linux OS. The whole project, including file system migration codes, testing codes, and annotations, there are totally 2, 3, 3, 4, 5 lines of code. Evaluation results shows the benefits of each techniques. Generally, HNFFS improves 20 to 16% recovery performance compared to JEF2, and HNFFS saves about 93% memory while achieves 2.3 times and 6.04 times write throughput compared to JEF2 and SPIFs. Our presentation is over. Thanks for watching.
Hello. Thank you very much, ENT. And any question here?
As far as I know, Jeff2 is originally designed to support sequential write workload as it typically happens in IoT workload like camera recording or sensor logging. So it seems that the work aims to support the workload with many random writes and to reduce the overhead. So what kind of workload can best benefit from the new file system design? What kind of application can benefit the most? Thank you.
Hello, can you hear me?
Yes.
Okay, that's a good question. For workloads, we think that because our write is done sequentially totally, because we format all the data into a node and sequentially write this node. So any workloads is fine, but but our workload, our file system are suitable most for those workloads which has several small node write, and we can save many of memory in that case, and perform much better in this workload. And for those applications, I'm sorry, our work doesn't consider this. We'll further we'll work further on this topic in our future work. That's all.
Here's another question. What is the space consumption of ESS? Because you somehow need to consume extra space to record that in the NOR flash.
Yes. That question is included in our paper, and because we only maintain a pointer to the nodes in the sector, so our consumption is lower, is relatively low, about 12% of total NOR flash space.
Thank you.
Okay, thank you.
Okay, any other question? Okay.
Thank you for your presentation. And I'm based on my knowledge, the JFFS tool is published and developed many years ago. About 2005. So I'm curious about is there any other works you can compare in your performance evaluation, because you are compared to the very basic file system. Thank you.
Yes, the file JEF2 is old file system. That's really the true. But it is representative. And even nowadays, there are many embedded systems use JEF2 as their file systems. Besides, there are many new embedded file systems emerging today, including LittleFS and other file systems. But migrate this file system into Linux OS is quite a large work required. So in this work, we only compares JEF2 and SPIFs. For the represent two kinds of file systems. JEF2 represents the file system that maintains the index structure in the DRAM, and SPIFs maintains its index structure in the NOR flash. So we'll work further to compare, to migrate more embedded file system into Linux OS, and so that we can compare more file system with our HNFFS.
Thank you.
Thank you.
Any other question? Okay, I have several questions. The first one is that in your solution, it needs to do the defragmentation, and we cannot see the evaluation to this part in your experiment. Can you talk more about the this part? I mean, the overhead of your defragmentation. Thank you.
Defragmentation means the merge tree merges those small data into a large one.
Yes. Yes.
Okay. This is indeed the problem of multiple tree design, and this part is unfriendly to NOR Flash. Unfortunately, we haven't made this part evaluation. But this is quite a problem. Yeah. One available solution that strikes me is to maintain this small data in the DRAM, and thus we can mitigate this problem. But this introduces this damages data integrity. So this problem is quite difficult to solve. So we'll work further on this problem in the future.
Okay, thank you. And the final question is that your design seems that it can be worked on NAND flash memory as well. Can you explain whether your design can be implemented on NAND flash or not, and what's the reason? Thank you.
I beg your pardon. I beg your pardon.
Because your design targets NOR flash, but it seems that your design is still workable on NAND flash, and I'm wondering whether your design is suitable for NAND flash. If yes or not. I mean, what's the reason? Yeah.
Our work is NOR flash is usually used in resource-restricted IoT scenarios, but NAND flash can use more. NAND flash can be integrated to the systems that can use more resources. So our file system should consider both resource consumption and performance behavior. So in our design, for example, adaptive GC, we combine foreground and background GC. But set two rules to this background GC to restrict its resource consumption, including activation threshold and triggering time interval. So I think our work is because NAND flash it has internal. Many NAND flash nowadays has internal FTL and wear leveling, so the wear leveling algorithm we proposed might not be so useful in NAND flash file system. Besides, due to the memory usage in NAND flash could be much more, so we even don't need to merge this small node in the runtime for reducing its memory usage. Does that answer your question?
Yes. Thank you very much.
Okay.
Thank you, Yanqi, and let us thank Yanqi again. Thank you.
Thank you.
And thank you very much to join us for today's session. And our session ends here. And let's come back at 1:30 p.m. for the next session. Thank you.